Hello and welcome to another video of Intro to Machine Learning. In this video, I'm talking about decision trees. We'll talk about the intuition, mathematical interpretation, and finally a complete Python implementation. So what are decision trees? So the decision tree algorithm belongs to the family of supervised learning algorithms, and in specific, I would say it belongs to CART. You might have seen that term before. That stands for classification and regression trees. Um, the decision tree algorithm can be very useful, as we said, for classification and regression problems both. So it can be applied to both. The goal is to create a training model that stratifies data. I would like to emphasize that term. Why? Because it divides the feature space into rectangles or boxes, as you can imagine, depending on what's the dimension of the data that you're working with. And a better way to understand this algorithm is to think about a flowchart of decision branches. Let's look at an example to better understand what this essentially means. Again, I'm looking at the age and salary data that corresponded to whether a person bought something or not. Let's say if we could visualize this somehow. So this is not the actual data. I'm just like making this up so that we understand how this decision tree algorithm works. Well, let's say I have ages of customers, maybe 18, 23, 28, 32, and so on, sorry, 33, and so on. I'm just, as I said, making up this data obviously doesn't exactly look like this. I'm just making up, let's say we have this data, so 100K, 150K, 200K, and so on. So we have salaries and ages, and the output or the outcome variable is whether the person purchased something or did not purchase something. So not purchased is NP, and excuse me, P stands for purchase. Okay, so let's say this not purchase points. So these would be like data points, right? I'm just like making it more explicit, but maybe it is like it looks somewhat different here, and then P. Let's say that like my data looks something like this, right? And maybe an NP is here, P, maybe a P is here, I don't know, right? And so on. Okay, so the way I'm going to like stratify this data is that I look at this entire set of not purchased and purchased points throughout the data, and I clearly see that there is this line that I can draw from top to bottom somewhere here at, like, let's say age 25, right? So if I'm able to draw that line here, I can actually divide the people who did not purchase versus the people who purchased into two parts, right? And let's say there were more not purchased here. I know I'm making it up just to make things clear how this works. So I found that I made this first split, and then I saw there are some, like, there is this another bunch of not purchased here. So I can again make a split so that when I come with a new point, and let's say the new point lies here, I can say that this is the not purchased region, or if the new point lies here, I can say this is the purchased region. Okay, so the split must result in rectangles, or if this is a higher dimensional space, this must result in boxes. Now, a better way to interpret these splits, and these splits may go on and on. I'm not saying that this stops here. It depends, and we'll talk about that as well. But this is the general idea, to split the feature space such that we can have let's say there were two response variables, so we can, depending on the response variable, stratify the data. Now we can also visualize this split in terms of a flowchart, which usually we do. So for instance, what we did here, if you just look at it, well, let's say the salary is around 175K, right? So there was a split at 175K. There's a split at age 25. In order to better visualize this, let's say we began with the variable age, right? That's the first split I made. And I made the split at age equals 25. So I can create this decision block saying if age is less than 25, whether that's true or not, yes or no. Yes, age is less than 25. So are you going to purchase or you're not going to purchase? So age less than, let's see. If age is less than 25, most likely you lie in the region where, okay, you're not going to purchase, right? And so then I stop. Let's say age is greater than 25. Then there are both things that can happen, right? Purchase and not purchase. So we'll have to think about the other feature variable, sorry, the other feature, I would say, or the other variable, which is my salary, right? So is salary greater than or equal to 175, right? Yes or no again, right? So we can have a yes or a no. So if it is greater than, right, here, then it results in a no purchase, mostly, right? Mostly, and we'll come to that, like how do we decide? And then if no, then it results in a purchase, right? So in terms of terminology, this is called the root node, where we started. The attribute or the feature or the variable from where we started splitting is the root node. And eventually we arrive at our answer of target variables, which is purchase or no purchase. Like those are the outcome variables. So these are known as the leaf nodes. And this, as you can tell from the structure itself, looks like a tree, although it's like an inverted tree, I would say, right? Because if this is the root and these are the leaves, so obviously this is an inverted tree, and that's where the name decision tree comes from. Okay, so this was a general idea of a decision tree. Let's talk a little bit about the details of the tree building process. How did we arrive at these answers, right? So like essentially we divide the predictor space into n non-overlapping regions. That's important. If there is an overlapping region here, let's say if the feature space looked something like this, like these kind of boxes, then this is not the correct way of creating it, because this should be clear in terms of like both the variables, like where does this region lie, right? So we cannot have such an overlapping kind of regions. And then every observation that falls in a given region, let's say R of I, then based on that we make the prediction, which is based on the mean of the response values of the training observation. So when I write the mathematical equation, maybe that will make things clear. So basically my goal is to minimize the sum squares for every box or every rectangle. So let's say I have like all these uh, from I to N. So these are the regions. I have like I to N regions or N rectangles. And for every observation in, let's say, a given region, I should be minimizing my value. So this is um, the actual value minus the mean for that particular region, calculated mean, and I have to minimize this. So that's my goal in this algorithm for every region. This is the mean response of the training observations within the ith box, right? So I have like, let's say n boxes. So I'm going to sum up this difference for each box. So this is my goal, right? So maybe this makes things clear. Some basic definitions. What's really happening in when we are creating these regions is that we are trying to reduce the randomness of every region. So that randomness is often termed as entropy. So entropy is a measure of the randomness in the information being processed, which is like my data, right? The higher the entropy, the harder it is to draw any conclusions from that information. Just think about this information, this definition right now as something that is a measure of how random your data is, and how would you segregate it so that you can reduce this randomness. There is another basic definition that we should be aware of that's called information gain. It's a statistical property that measures how well a feature separates the training examples according to their like target classification. For example, in our case, it was purchase or no purchase. Okay, so making a tree that we just built is all about finding that particular feature that returns the highest information gain and the smallest entropy. Obviously, we want the least randomness in that particular region and the most information gain, which means I should have, let me go back, the max split here, this thing, right? I split this in such a way that I could segregate the no purchase and the purchase really well. So here I gained a lot in terms of the information that I'm getting from that split. So think about that in like information gain in that sense, like how much information I gained and I minimized or really reduced the entropy, the randomness in the data that existed overall. Okay, so this helps us decide where should my algorithm begin from, right? So like every time I begin with a root node, I have to decide what that root node should be, right? And in each iteration of the algorithm, I should iterate over the most unused feature of the data, right? I have to figure out, okay, this feature hasn't been used, but then I also have to calculate the entropy and the information gain of that feature. Now, based on that smallest entropy and largest information gain, I have to select the feature. Think about a data set that has like n features, lots of features, and then deciding where to begin from, what is going to be my root, is a difficult question. Well, the good news is that it has been answered because there has been a lot of research in this area, and then there are ways of selecting the features, and there are many criteria that are involved in selecting the features. So we know two criteria already, that's entropy and information gain. When we do this implementation in Python, we will do based on entropy. So basically our model will select our features based on the least entropy and the highest information gain. But there are other criteria that are available as well, and you can implement them as well. But we are focusing on entropy and information gain. So basically just think about it in layman terms, trying to reduce as much randomness as possible in a given region and increase as much information as I can get by that particular split in a given region. Okay, so a little bit more details of the algorithm. So it's you can tell that it's practically impossible to consider every possible partition. What happens if I have this like x1 and x2, and then let's say I did a split here, right? And you can tell that like real world data won't be as well behaved, right? So I might do lots of splits, right? And just like keep going on, right? And nobody's stopping me. And the way this algorithm is working is it follows a top-down greedy approach, and that approach is called recursive binary splitting. Basically, at every step, the best split is made at that particular step rather than looking at my overall result. So the way I was splitting, remember in our age and salary, was okay, I thought this is a good split. Let me split here, right? Because I'm getting most out of this particular split, which is why this is known as a greedy algorithm. It doesn't look at the overall good of how we are going to get the overall results, but rather what is happening at that particular step. That's why it's a greedy algorithm. Okay. Another issue sort of or a negative of decision trees is that they can create over complex trees that do not generalize the data well, as you just saw in this example here, right? I could go on splitting and so basically I'm overfitting my training data, right? So we might overfit them sometimes. That results in poor test results, which means higher variance. Now you know the difference between variance and bias, and you know this will introduce higher variance. So a few mechanisms are available to us for dealing with these issues, such as pruning. What pruning does is that you grow a tree as much as you can, and then you prune it, which means you remove certain parts of it because you felt that these were just an added cost. So how that is done is by setting the minimum number of samples required at a leaf node. Basically, you cannot go on and on if you think about a tree, right? You cannot go on, and let's say you are deciding based on like one observation only, because that's you kept splitting this space, and then you arrived at a box that has just like one observation. So that's like overfitting the data, and obviously it will not generalize well. So for that, there's something called pruning, in which we set that this is the minimum number of samples below which I won't split or I won't get a new region or a box. Okay, so that's the way we prune a given tree. There are many ways of pruning, so you can also set a maximum depth of the tree. So basically, I'm not going to go below this level, right? And so I can do a good job of balancing my variance and bias. So that's called pruning. Okay, and then finally, we are coming to our Python implementation of a decision tree. Just wanted to let you know that the classifier that we use, the class that we use is called the decision tree classifier in scikit-learn package. And the criterion we are using is entropy, and you know that there are other criterion available as well. So entropy is going to ensure that the way our features are selected and the way the splitting happens is based on the minimum entropy and maximum information gain. That's what we're doing here. Okay, let's quickly go to Spider. Again, if you remember, I'm using the same data, the social network ads data that has age and salary, and based on that, we predict whether the person is going to purchase something or not. Okay, this is known to us, all of this, importing NumPy. We're not plotting anything yet because the plot becomes really complex. I'm not going into that yet. But yeah, we are using the rest of the libraries. Let's import them. And then I'm doing a train test split. We have done all of this here and feature scaling. So this is all known to us. I'm not talking about it again. Right, so we scale the features. This is important. Now I imported the decision tree classifier as I said earlier, and then created an instance of this class. And notice the criterion I'm using is entropy and fitting the model. Okay, so in my training set, of course. Okay, so that's done. Let's predict it for that one point that we've been predicting for with all our models before. So notice it says that this one is going to purchase that item. And if you remember in our previous models, this has been predicted as 0, that the person is not going to purchase that item. So that's slightly different from what we've been getting. But let's look at the accuracy to better sort of compare other models with this one. So here I'm predicting, so we have talked about this before. I'm not going into the details, but notice the accuracy that we get with this model is 0.91. If you remember with the naive based classifier, we got 0.90. So it's slightly better than that. This code is provided in the link below in the description box. So that's it for decision trees. See you in the next lecture.